to give this talk because Nick Horspool from GA had to attend to some urgent business. Anyway, so I'm going to talk about SUDAT, which is a tsunami modeling application. The goal of SUDAT has been to transfer the capability to model tsunamis from a few experts to many non-experts. So it's a partnership for organizations. Geoscience Australia is not up there, but I work for an organization called OpenGeo. OpenGeo is a social enterprise nonprofit which offers commercial support for a lot of the open source geospatial stack. So things like OpenLayers, GeoServer, PostGIS, GeoNode, things like that. So we're a nonprofit. All the profits are reinvested into supporting the goals of our parent organization, which is open government and citizen involvement in civic planning. And so NCI, I'm sure most of you are aware of what NCI is. It's a facility at the ANU that offers high-end compute services to researchers and government agencies in Australia. And one of their offerings is the OpenStack-based cloud, which is what we're using for this project. That's is quite similar to Amazon Web Services and other commercial clouds. And then AFDR, AIFDR, is an offstate facility in Jakarta, which is working on capacity building with local Indonesian researchers and disaster managers to increase Indonesia's capacity to prepare for and respond to disasters. So let's see here. So the problem is that after the 2004 Indian Ocean tsunami, country came to a big realization that we need to sort of prepare tsunami inundation maps and evacuation plans. In Australia, there's 2.2 million people that live within 3 kilometers of the coastline, but only about 20 localities have prepared inundation maps and evacuation plans based on scientific modeling of inundation. So in Indonesia, the numbers are like 2 orders of magnitude larger, and there's basically no evacuation plans that have been prepared that are backed by scientifically modeled inundation maps. So in Australia, prior to the release of the SUDAT tool, there were only 2 agencies that had the expertise and ability to do tsunami modeling: Geoscience Australia in Canberra and the Bureau of Meteorology here in Melbourne. And even then, only a handful of researchers at each agency could do the modeling. So basically, there are far more Australian sites required expertise than there were experts available to do the modeling. So we've worked on a new tool that it hinges on the ability to distribute the knowledge of tsunami experts and local planners. So the first iteration of that effort was SUDAT-1, which was a desktop tool that allowed flood model experts to access pre-generated tsunami model data directly. This increased access to the wider population of flood modelers, but still required experts. And what was truly needed was a way for non-modelers, like emergency managers, planning officials, land use staff, to directly create detailed tsunami inundation maps for coastal communities. So using the new SUDAT system, anyone can create a hazard map with just a few hours training, and any event can be simulated from a small event with a 50% probability over 10 years to a large event with a much greater wave height that may occur once every 1,000 years. So after the SUDAT-2 release, we have disaster managers from 9 different localities in Australia that have been trained, and 2 from Indonesia, and each of these contribute their local expertise, knowledge, and data using the new SUDAT web app. So the SUDAT web app is made up of, it's a sort of mashup of 3 distinct pieces of technology. The first is the scientific tools and data. Primarily, it's the probabilistic tsunami hazard assessment, which I'll talk about more in a second, and the Anuga hydrodynamic modeling library that the ANU and GA built. The second component is web-based geospatial stack, which is based on tools from OpenGeo, GeoServer, GeoNode, PostGIS, and GeoServer. And we're using cloud computing resources from ANU at the NCI, which are based on OpenStack. And all these components are free and open source. So the data flow works like this. They run the PTHA, probabilistic tsunami hazard assessment, which basically models thousands of events, which an event is an occurrence of slip on a subduction zone fault in the deep water that propagates, and the PTHA propagates that waveform to the 100-meter water depth at a particular hazard point offshore in Australia. And this gives us an event database that is a pre-computed set of wave height. So for a particular event, a wave height at a hazard point. And they've modeled it for about 75,000 events on faults around the Pacific Rim. And from there, the SUDAT app is used to set up a simulation of that event and propagate that wave onto the land using high-resolution elevation data, and this generates an inundation map for a particular area of interest. So this is the sort of cloud, how the cloud's set up. The green there is all takes place on one virtual machine, and the red are basically temporary virtual machines. So users log into the web portal app, upload their high-resolution DEM data. They construct a simulation using the pre-computed event database. They run that simulation using the NUGA on the NCI cloud on those transient VMs, and then they can share their data with others using the GeoNode platform. So take a closer look at the actual application. So the hazard points are the ring of points around Australia. So you select a hazard point, select the return period up here. So return period is the inverse probability of the event. So 1 in 100 year event is a small wave, and 1 in 1,000, 1 in 10,000 larger event. So this lets the researcher do basically what's called deaggregation. So you see the red dots on the Poiseuille subduction zone up in the Hebrides. Those are it's percent contribution to hazard. So for that particular highlighted hazard point, those are where the likely source of tsunami come from. So a specific event is selected. We can't see it's the fourth column here. So you have a particular event for size, maybe size 9 or magnitude 9 earthquake. Go to the next step, which is graphics looks a little strange, but basically you select the area of interest. You can draw that using the web-based tools. In the past, usually this was done with ArcGIS or some tool, and you had to do a bunch of manual conversions before you sent them off to a NUGA. But now this is all done inside the web app. You can upload shapefiles or draw the area of interest. So you can select interior polygons like the one in the center there that's used to select areas for further refinement inside of a smaller area of interest. And then the user selects, and that graphic's also here not working correctly, but anyway, the user uploads their own elevation model. The accuracy of the results is a function of the quality of the elevation data. So each of the researchers in their local area has higher resolution elevation data that they upload. The key aspect of this tool is that each local disaster manager has access to high resolution data for their area, and they upload it. And the next step is they run the simulation. So at this point the job is queued up in the system, a virtual machine on the OpenStack cloud is provisioned and configured to run the job, and a work package is extracted from the system and sent to the virtual machine for processing. And we're using AMQP, RabbitMQ, to do messaging between the virtual machines and the main web app. And when the job is complete, the data is pushed back to the main site. The user gets an email. Data has been loaded into the GIS. They get this email. They click on the link in there, and this takes them to graphics here. Also, I should have taken a look at this before. But anyway, they get a result map, and the metadata there is it's really scrambled. In any case, the metadata is populated with the detail about the event that was simulated. Its metadata is served up in a standards compliant way using CSW, and the data can be downloaded as GeoTIFF, and it's also served up as WMS, WCS, OGC compliant standards, and then the user can set permissions on those data to make them private, share them with other people in their group, or make them public. From there, they can create composite. This is using GeoNode platform. They can create composite maps with their results and other data, and share those results by embedding the map in other websites, wikis, that sort of thing, downloading or sharing it with others using web services. So just to summarize, SUDAT is a web application that provides scientific data and tools to increase the capacity of state and local governments to conduct tsunami modeling. So again, they're taking the capacity that used to be the domain of a few experts and pushing it out to many non-experts. The web server and scientific computing is hosted in the cloud at NCI, and that provides scalable and cost-effective computing resources that are shared with other people. So there's no large upfront cost for the disaster managers in localities. And the spatial data is managed through the GeoNode platform that facilitates uploading, editing, sharing, and everything is standards compliant and open source. and this framework can be applied to other scientific applications, but it's also been integrated with other tools that AFTR and AusAid are working on for risk calculation. So risk is a calculation from hazard data like the tsunami exposure data, which is buildings and where buildings and people are, and some damage function, and that's used to calculate risk. And so this fits in with these other tools, also the global earthquake model, also using the same platform. So that's it. This is our first workshop that we held with local disaster managers from around Australia and a few from Indonesia. So that's it. Any questions? Do my best to answer them. Yeah. As far as I understand, we have some national level data. I'm just one of the developers on this project, but yeah, we have some national level data. But then each of the localities upload stuff like up to 1 meter DEMS or. Say that again. Yeah, but I mean, most of the stuff that they upload are small for their locality, like the Bateman's Bay may upload their data, or somewhere in Brisbane may upload their data, but we have nationwide data. I think it's 30 meter DEM that we've been working with for the, but. Yeah.
I assume that this had some sort of temporal dimension, because what sort of time period do people have between events and you providing data to a disaster?
This is primarily used pre-event, so it's used to simulate what would happen for an event of this magnitude, and generally used to create evacuation plans. So it's pre-event planning. It's not generally used for post-event. I mean, these simulations can take hours or days to run, but the kind of goal is for the locality, that's small municipal area or disaster planner in some area, to simulate several events, get the inundation map, sort of look at how those look, some general patterns that emerge from those by looking at several inundation maps, and create an evacuation plan. Maybe they say, oh, well, this particular building here is at risk. Maybe we ought not to have a school here, or that sort of thing. But it's just generally pre-event, not post-event.
Some of the analysis of that was that yes, people were prepared for minor events.
Yeah.
But people didn't believe the data.
Right, and they didn't believe the posts that were up on the hills that said, don't build your house below this point, right? But I mean, that's the kind of thing, is to do some modeling simulation pre-event, find out where the maximum inundation will be, and plan accordingly ahead of time. And that's especially what they're trying to do in Indonesia. One of the chief drivers of this project is the AusAid facility there in Jakarta, and they're really trying to push down local capacity to disaster planners in Indonesia and say, well, maybe you ought not to have a clinic here or a hospital or a school. Maybe we should move those out to higher, and they have some data, some scientific data to back that up and show them, well, we've ran a model, and this is where the inundation would happen from an event on this fault, which, based on our research, may happen every 100 years. So we should do that.
One more question.
Mm-hmm.
Why there are signs everywhere around the street
Mm-hmm.
pointing you to the tsunami evacuation.
Right.
But do you think that
Yeah, we have them where I'm from in San Diego. We have them as well. So it's like, yeah, and I think that's unfortunately, I'm just a software developer here. Nick's not here to answer all of your specific questions about Australia, but yeah, I gather that is the goal, that push this tool down to local planners at the local level and let them run some models and say, oh, well, we ought to move, we ought to place some signs here and teach people to move back away out of this area. This is what's going to be inundated on this particular type of event. So, yeah. More questions?
No more questions. We should thank the speaker. And I have no idea what